In this video I will cover thread safety and synchronization. But first let's start from the hardware memory architecture and Java memory model to understand why we need synchronization in Java multithreaded applications and where. Modern computers has several CPUs, and several CPU cores. So in this case, in the multi-threaded applications on Java, for example, these threads can work in different CPUs and work simultaneously, they're not depending on each other. So CPUs can have CPU registers and CPU cache memories and Java main and the access to the main memory. CPU has faster has access faster can faster access to the CPU cache memory and fast and it can just faster than it to access to the CPU register. So to just optimize their work, it will just partly copy from the main memory data to the CPU cache memory and partly from the CPU cache memory to the CPU registers. Java memory model. Java memory model was revisited in fifth version of the Java and used still now. So Java memory model used internally in the JVM divides memory between thread stack and heap. So thread stack contain the information about the methods which call it in this thread. So each thread has its own thread stack. So thread stack contains information about methods, about variables. So any primitive variables save it fully in the thread stack, but reference variables can have its references saved in thread stack are content saved. So these objects saved in the heap with its members. Also, any object member, so even if it's primitive or not, it will save it in the heap. Any local variables with primitive type save it in the thread stack. Static class variables are also stored on the heap along with the class definition. Object on the heap can be accessed by all threads that have a reference to the object, while thread stack can be accessed only its owner thread. So Java memory model and hardware memory model architecture are different. The hardware memory architecture does not distinguish between thread stack and heap. On the hardware, both the thread stack heap are located in memory. Parts of them can be located on the CPU cache memory or CPU registers. Let's see Java memory model in example. So in this case, we have a run method of the threads which calls method 1 and method 1 calls method 2. So method 2's definition here. Okay, So each thread executing method 1 will create local variable 1 and local variable 2 on their respective thread stacks. The local variable 1 variables will be completely separated from each other, only living in each thread stack. One thread cannot see what changes another thread makes to its copy of local variable 1. Each thread executing method 1 will also create their own copy of the local variable 2. However, the two different copies of local variable 2 uh, points to the same object on the heap. So, it's here. On the heap, the code sets local variable 2 to point object references by static variable. There is only one MyShared object which the static variable points to. The MyShared object instance is also stored on the heap. It corresponds to object 3 in the diagram. Object 3 in the diagram. So object 2 and object 4 represent its members like this. Okay. Also, method 2 creates a local variable named local variable 1. This local variable is an object reference to an integer object. The method sets the local variable 1 reference to the point to a new integer instance. The local variable 1 reference will be stored in one copy per thread. Thread executing method 2. The two integer objects instantiated will be stored on the heap, but since the method creates a new integer object every time corresponding to the method is two threads executing this method will create separate integer instances. So it's in the picture it's like object 1 and object 5. And also that two members of variable in the MyShared object of type long, which is a primitive type, but it's a variable, it's a file of the object. MyShared object variable, so they are stored in the heap. So let's see about thread safety and shared resource. Code that is safe to call by multiple threads simultaneously is called thread safe. If a piece of code is thread safe, then it contains no race conditions. Race conditions only occur when multiple threads update shared resource. Therefore, it's important to know what resource Java threads share when executing. Local variables. Local variables, if it's stored in the thread stack. Local object references, so references stored in the thread stack, but it's content stored on the heap. But even this, in this case, it will be thread safe because it will not be available to the another threads. So the reference is available for only the owner thread. Object member variables. Object member variables are stored on the heap along with the object. Therefore, if two threads call a method on the same object instance and this method updates the object member variables, it can take different values. So the method is not thread safe in this case. So also there are mechanism called CPU cache coherence. So in this case, all variables visible to the thread which are stored in support registers, will be flashed to main RAM. On the way to main RAM, the variables its cache coherence methods to make sure that all other CPU's caches can see the variables in the first CPU cache. The hardware may even choose not to flash the variables all the way to main memory, but only keep it in the CPU cache until the CPU cache storing the variable is needed for other data. At that time, the CPU cache can then be flashed to the main memory. However, for the code running on CPU, this is not visible. As long as it gets the data it requests from any given memory address, it doesn't matter if the returned data only exists on CPU cache or whether it is also exists in the RAM. You don't have to worry about CPU cache coherence loss. There is of course a little performance hit CPU cache coherence, but it's better than writing the variable directly to the RAM. Visibility of shared object. If two or more threads are sharing an object without the proper use of either volatile declarations or synchronizations, updates to the shared object made by one thread may not be visible to other threads. Imagine that the shared object is initially stored in main memory. A thread running on CPU one then reads the shared object into its CPU cache. There it makes changes to the shared object. As long as the CPU cache has not been flashed back to main memory, the changed version of the shared object is not visible to threads running on other CPUs. This way each thread may end up with its own copy of the shared object, each copy sitting in different CPU cache. Also we have problems called race conditions. So race conditions means that if two or more threads sharing an object and more than one thread updates variables in that shared object, race conditions may occur. Imagine if thread A reads the variable count of a shared object into its CPU cache. Imagine too that thread B does the same but into a different CPU cache. Now thread A adds 1 to the count and thread B does the same. Now var 1 has been incremented 2 times, once in each CPU cache. If there is increment had been carried out sequentially, the variables will be value plus 2. But two increments have been carried out concurrently without proper synchronization, so we will get value plus 1 plus 1. To solve this problem, we can use synchronized block or volatile blocks. Race condition has two versions, so like here or like here. So in this case, the first case is about, so this operates, this expression operates three different process. It reads this count, so here reads this count from the memory and adds value and writes to this count memory new value. So in this case, when first thread reads this count and then adding value, while it adds value, can access second thread, which will just read this count, the old version of this count, and adds another value. So uh, And when writes it, the first one writes firstly, but second one will be overwrite it. So in this case, it will have the wrong result. Checking then act version is same. So in this case, when it this code when checking the threads gets same result, but when operating only one will succeed. So also we have memory consistency errors. So it's the same. Memory consistency error occurs when different threads have inconsistent views of the same data. So for example, in this case, static boolean say hello. So say hello can be written, can be set true, but this thread will cannot see this change. So let's see what will be resulted in this code. So in this case, we will not get these messages. So because memory is inconsistent. Memory consistency errors has been appeared. Also, new tuples have the ability to execute instructions in parallel if these instructions do not depend on each other. For instance, for instance, here, two expressions are not depend on each other, but here it depends because A and A here is same. But in this case, we can just do three operations simultaneously. So it will quit the optimized version. Also, Java provides thread local class. So thread local class enables to create variables that can only be read and written by the same thread. Thus, even if two threads are executing the same code and the code has a reference to the same thread local variable, the two threads cannot see each other's thread local variables. Thus, the Java thread local class provides simpler way make code thread safe that would not otherwise do. So let's see example. In this case, this formatter is created like here, but it was changed like here. So in this case, this method, in this case, it will not, it will change it in several threads, and it will not be able to available to the other threads, even if it's this changes. So let's see. For example, this changes this static variable, but thread 3 doesn't know about it. So this doesn't know about it. Even this doesn't know about it. Also, we have Java happens before guarantee, so with synchronized and volatile keywords. So it's the rules govern how the Java VM and CPU is allowed to reward the instructions of performance gains. So it's like synchronized keyword. Synchronized keyword can be uh, set to the instant method, set to the static method, or we can create synchronized block. The object taken in the parentheses by the synchronized construct is called a monitor object. So monitor object. So in the first case, when we create instance method synchronized, uh, monitor object will be this here. In this case, when we create static methods with monitor static synchronized methods, it will be just the class of this method. So in this case, interference in memory consistent errors can be avoided by the following two things. Only one thread can read and write shared variable at a time. When one thread is accessing to a shared variable, the thread should wait until the first thread is done. This guarantees that the access to shared variables is atomic and the multiple threads do not interfere. Whenever any thread modifies a shared variable, it automatically establishes a happen before relationship with subsequent reads and writes of the shared variables by other threads. This guarantees that changes done by one thread is visible to others. Luckily, Java has synchronized keyword using which we can synchronize access to thereby avoiding both kinds of errors. When a thread occurs intrinsic lock on an object, all the threads must wait until the lock is released. However, the thread that currently owns the lock can occur it multiple times without any problem. This idea, uh, allowing a thread to occur the same lock more than once and it's called reinforcement synchronization. So happens before visibility guarantee of the synchronized objects. Synchronized keyword is when a thread enters to the synchronized block, all the variables visible to the thread are refreshed from main memory. And also exit visible guarantee is when a thread exits synchronized block, all variables visible to the thread are written back into main memory. Also happens before guarantee where Java synchronized block beginning happens before where none of the reads of the variables can be rewarded to appear before the beginning of the synchronized block. None of the writes to the variables can be rewarded to appear after the end of the synchronized block. Volatile keyword. The Java volatile keyword is used to mark a Java variable as being stored in main memory. More precisely, that means that every read of a volatile variable will be read from the computer's main memory and not from the CPU cache, and that every write to a volatile variable will be written to main memory and not just to the CPU cache. Actually, since fifth version of the Java volatile keyword guarantees more than just that volatile variables are written to and read from the main memory. So, visibility guarantee says that when you write to a Java volatile variable, the value is guaranteed to be written directly to the main memory. Additionally, all variables visible to the thread writing to the volatile variable will also get synchronized to the main memory. When you read, the second rule says that when you read the value of a Java volatile, the value is guaranteed to be read directly from the memory. Furthermore, all the variables visible to the thread reading the volatile variable will also have their values refreshed from main memory. Java volatile happens before guarantee says that a write to a non-volatile or volatile variable that happens before a write to a volatile variable is guaranteed to happen before the write to that volatile variable. A read of the volatile variable will happen before any subsequent reads of volatile and non-volatile variables. Leave lock is okay. Let's start from the deadlock. Deadlock occurs when there is more than one thread each waiting for the resource held by another, such that a cycle of resource and occurring threads is formed. The most obvious kind of resource is an object monitor, but any resource that causes blocking, such as wait notify can quality. The deadlock happens if at the same time one thread is trying to transfer from the first account to the second and has already acquired the lock on the first account. Thread is trying to transfer the second account to the first one and has already acquired the lock on the second one. Techniques for avoiding volatiles, avoiding deadlock is avoiding nested locks, lock only what is required and avoid waiting indefinitely. Okay, let's see about leave lock. So leave lock is same as deadlock, but in leave lock, two or more threads keep on transferring states between one to another instead of waiting indefinitely as we saw in the deadlock examples. So consequently, the threads are not able to perform their respective tasks. So let's see the example to the deadlock. So in this case, deadlock sample. So in this case, we have pen and paper, and the two threads synchronized. It's synchronized in paper. It's synchronized on the pen. And when we start it, we can see what happens. Thread 1 holds pen. And it wants and it can't access to the paper. Thread 2 holds paper and it can't access the pen. So the video is over.